When first learning about related rates, make note that a derivative is a rate of change, and that when working with rates of change, it must involve a derivative, usually with respect to time. To start out here, whenever you're working with related rates, please always make a sketch of the diagram. So we sketched a sphere in this example to label any unknown information. This example is about air being pumped into a spherical balloon, and the only dimension we need to label is the radius. And the rate at which that is changing is 5 cubic centimeters per minute. And we're going to interpret that as the rate at which the volume is changing. And I'm going to make note of that given information as well. We have dV dt equals 5 cubic centimeters per minute. That's the rate at which the volume of the air being pumped into the sphere is changing. Next, we want to make use of an equation. You'd want to start out with your volume equation since we want to make use of the volume of the air. Volume of a sphere is 4/3 pi r cubed. And then the last sentence mentions that we need to determine the rate that the radius of the balloon is increasing, which means we will find dr dt, the rate at which the radius is increasing with respect to time, when the radius is 10 centimeters. So we'll make use of that 10 centimeters at the end of the process because you got to work with the radius r as a variable when you're taking its derivative. Let's get started with that derivative now. So we start with the volume equation, take the derivative of volume with respect to time. On the left-hand side, we will have dV dt equals, on the right-hand side, the radius is cubed. So the radius being your variable, on the right-hand side, we're going to do the power rule and bring the 3 down in the very front. Multiply that by 4/3 pi, the constant, which is not changing, r squared, subtracting 1 from that power using the power rule. But don't forget to multiply by dr dt, the derivative of r with respect to time, because the radius is changing in terms of time. We can simplify that by crossing out the 3's. Next, substitute any information you know. dV dt is 5 equals 4 pi r. We will make use of the radius being 10 at this instance of time. We're plugging in r equals 10 because we already took care of finding dr dt. dr dt is on the right-hand side of that equation. That's what we are trying to solve for. We want to find the rate of the radius changing with respect to time. So let's isolate dr dt by dividing each side of the equation by 4 pi times 10 squared. This is the quantity we are looking for. And plugging that in, 5 over 4 pi 10 squared is approximately 0.004. And make use of units here. The radius is in terms of centimeters and time is in terms of minutes. So we will call that approximately 0.004 centimeters per minute. So don't get confused by the units. Make sure the ratio of the units represents dr dt or whatever quantity you're finding. So make sure that your radius units are on the numerator, hence the centimeters, and your time units are on the denominator, hence the minutes.